Hello, Integrated Math 1. Welcome to lesson 4.1.1a. We're doing module 4, topic 1, lesson 1, and we're doing just the first day, which is why we have part A on all of this. So day 1, yay! And we're just going to do activity 1.1 today in our workbooks. Do notice we're now in volume 2 of our workbooks. Make sure you're in the right place. Also note the page number. We're now on page M4-9. So make sure you're looking for that 4 at the front. So M4-9 in your volume 2 of your workbook, just to make sure you're in the right place. It'll make this all a little bit easier. So we're going to be talking about histograms in our lovely activity here. And remember, we were talking about the amount of lead in our water samples, right? And we said that if you go over 15 parts per billion, you start to have a problem. So according to the Environmental Protection Agency, the EPA, if more than 10% of tap water samples are greater than or equal to 15 parts per billion, then action is required to reduce the levels. Because again, if we go over that 15 ppb, which starts to be very unhealthy. And so if more than 10% of your water samples have that, it's required by law to do something about it, which is fair. Apparently lead poisoning people is, bad. So we don't want to do that. Now, we did, in our getting started activity, we did this lovely chart here, right? We made this lovely little chart. And according to the data that we collected in our getting started activity with our chart that we made, is action required to reduce the amount of lead in the water in the neighborhood? So go ahead and hit pause, take a look at what we've got, knowing that more than 10% of our samples have to be over 15. Are we required to do something about it in the neighborhood? Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. So I'm taking a look here, and I notice, I need my pen here, and I'm noticing here's 15, but I've only got one little sample that's over that, right? That's over that 15 parts per billion. So I don't know what's going on in that sample. Maybe it got contaminated. It could happen. But that's only one out of what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's only 1 out of 20 samples. And if we were to do that as a decimal, I do have a calculator for that. 1 divided by 20, that's only 0.05, which means it's only 5%. And we said that in order for action to be required, more than 10% of your samples have to meet that. Well, looks like only 5% of my samples are over that 15 parts per billion. So no, there are 20 data points and only one data point is greater than or equal to 15 parts per billion of lead. So this is less than 10% of our samples, so no action is required at this time. Now, the mayor of Greenville wants to analyze the levels of water for the entire city. He wants to analyze the lead levels for water for everybody. The frequency table, here I have a lovely frequency table, displays the data for the amount of lead in drinking water samples taken from sites all over Greenville. So 32 of the samples were between 0 and 5 parts per billion, 48 were between 5 and 10, 100 were between 10 and 15, 47 of those samples were between 15 and 20, and 23 of those samples were between 20 and 25. Now, this table is useful, and yeah, I can see 100 samples were between 10 and 20. But it's not easy to get a visual on it, right? It's not easy to get like an idea of what's going on. So while this frequency table is great, another way to display quantitative data is to create a histogram. This is one of our key terms today. So another way to display all of this data, the amount of data, when we say quantitative, we're just saying the amount of data that I have. Another way to do that is to create a histogram. And a histogram is a graphical way to display quantitative data using vertical bars. So we're actually going to make a bar graph. You might know a histogram better as a bar graph, but we're going to call it a histogram now. Now, the width of that bar in your histogram represents an interval of data that we often refer to as a bin, right? So a bin represents that interval of data. So like 0 to 5 would be a bin, right? 5 to 10 would be another bin of my data. So a bin represents an interval of data instead of individual data values, right? So the value shown on the left side of my graph here, on the left side of my table, I should say, the data value shown on the left side of the bin is the least data value in the interval. So in this bin, we're talking anywhere from 0 to 5, 0 being the least, 5 being the most. Sorry about that. My lights are on, emotion sensor. Now, the height of each bar. So we said that the width of the bar is the bin, right? 0 to 5. Here's my little bar. That's my bin. The height of each bar indicates the frequency. And frequency just means it's the number of data values included in the given bin. So if I'm looking at this first line, 0 to 5 is my bin. So my bin, the width would be from 0 to 5. Whereas my frequency says that I should go up 32. There should be 32 items in that bin. So that 32 is the height of my bar on that bin. So histograms are effective in displaying large amounts of continuous data or data that can take any numerical value within a range. So the idea is that the bin gives us the width and the frequency gives us the height of the bar. And we put all the bars together and it gives us a lovely histogram. So what I would like you to do is I would like you to construct a histogram to display the data in the table. Go ahead and hit pause, make a bar graph, right? Histogram, bar graph. Remember that the width of your bar will be the bin and the height of your bar will be the frequency. So go ahead and construct that histogram to display the data on your table, and then go ahead and hit pause to work that out and hit play when you're ready to check your work. So I'm making my histogram. I'm going to grab a couple different colors here. So we said that the bar was the width. So I guess that's going to be my x-axis. And then we said the height of our, and then we said the height, goodness gracious, is our frequency. So I'm going to do this right here. So our bins go 0 to 5, 5 to 10. So it looks like our bins are counting by fives, right? So 0, and then we go all the way up to 25. So 5, 10, 15, 20, 25. So I'll write that down, 10, 15, 20, 25. So here I have my bins. You can see 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25. Very lovely. I do need to put what the units are, and it looks like my bins are measured in the amount of lead in water parts per billion. So I'm going to write that down below. Amount of lead in water. And we said that's in parts per billion, so I'll put ppb. All right, now we said the frequency was the height, right? The frequency was the number of things that were in that bin, and that's our height. So that means that's going to be my y-axis, isn't it? So let me label my y-axis. I'm going to go, it looks like I go all the way up to 100. So I'm going to go up to 100 at the top here. And of course, we have 0 at the bottom. And let's just count by tens. 10, 20. That's no good. Sorry, I like it to be pretty. I mean, it's not going to be perfect, but I can try, right? So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Ooh, I did pretty good there. Okay, so we'll label that 10, 20. It's not perfect. But again, we're not looking for perfection on a histogram. We're using it, except I can't type right. See, this is what happens when Miss Scott writes and talks at the same time. Remember that our histogram, it doesn't have to be perfect. It's just trying to give us a visual of what's going on. That's all a histogram is doing, just trying to give us that visual as to what's going on. I hate it when my pen does that. So I'm going to fix it because I want it to be pretty. So there's my 80. That's better. Now, of course, this is our frequency, but I don't want to label it frequency. I want to put actual units on that. So remember what this was, that this was the number of sites, right? These were sites that we were taking water samples from, and 32 of those sites, 48 of those sites, 100 of those sites. So along the side here, I'm going to put number of sites. Because that's what our frequency is. And of course, this whole thing is telling us the amount of lead in drinking water in selected sites in Greenville. So let's go ahead and make some bars. I'm going to grab a different color here. All right, so first bin, 0 to 5. We know that's the width of it. And we know 0 to 5 went all the way up to 32. So I need to go all the way up. There's 30, so 32 would be a little bit past that. So I'm going to make a bar right here. There's my first bar. Isn't it pretty? There we go. So there's my first bar. Bin 0 to 5 went all the way up to 32. My second bar is from 5 to 10. So that's the next bin. And it goes all the way up to 48. So 5 to 10 goes all the way. There's 40, almost to 50. So hang on. So I'm going to go up, 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 almost to 50, cut across, and then down, 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 down to 10. And of course, there's my next bar. Yay. The middle bar then goes all the way up to 100. Oh my gosh, it goes all the way up. So 10 to 15 goes all the way to 100. So from 10, I'm going to go up, 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 up. This isn't a very good bar. It's not very straight. All the way up to 100 and then come down. Oh, I hope you used a straight edge. I don't have a straight edge here and you can see it shows. Oh, that bar is a hot mess. Okay, that's fine. You get the idea that it goes up to 100. Next bin, 15 to 20, goes up to 47. So here I'm at 15. I'm going to go up, 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 up. Not quite to 50. Kind of cut across here. And back down to 20. And there's my other bar. And last but not least, 20 to 25 is my last bin. That goes up to 23. So 20, I'm going to go, oh, sorry, babe. I'm going to go up to 20 and a little bit past it, cut across, and come down to 25. Here we go. Wow, that is a beautiful histogram. It would have been prettier with a straight edge. I won't deny that. Okay, so it's not the prettiest histogram I've ever made, but I'm pretty proud of myself. That's a respectable histogram. And again, it's not perfect. You can see it would have been better if I'd used a straight edge, but you get the idea. You can see the patterns and what's going on here. This actually gives us a really good visual on what's happening with these samples. I'm going to go ahead and erase all this and bring up this one. It's typed and pretty, and the book did it, and it's very nice. So yeah, we got something like this. So this gives us a good visual on the amount of lead in drinking water in selected sites in Greenville. So now that we have this lovely histogram, what conclusions can you draw from the histogram about the amount of lead in the drinking water of Greenville? Go ahead and hit pause, jot down some of your thoughts, and then hit play when you're ready to check your work. I had to turn the lights back on. All right. So I don't know what conclusions you saw, but I realized if I added up all of my frequencies, which was a little easier to do from the table, if I added up all of my frequencies, let's see, if I added all of those up and I was like 32 plus 48 plus 100 plus 47 plus 23, I was like, hey, there's 250 sites here. But I also realized, remember that the problem was that 15 or above, right? So I realized a few things. There's 250 of these. But when I counted it up, I realized that 180 of them, these three, boom, 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 those first three bins, when I added up those first three, that they were all below the level, right? So I was like, okay, so I can look at this and I can see from these three bins, that 100, that 48, that 32, if I added those up, I realized that 180 sites had less than the 15 parts per billion of lead in the drinking water. But that meant that 70 sites have 15 parts per billion or more of lead in the drinking water. Yikes. So Marcel created a histogram to display the same data. And Marcel's histogram, he looked at his histogram and he said, look, no action has to be taken to reduce lead levels in Greenville's drinking water. Is Marcel correct? And why or why not? Remember, 10% is the threshold. Go ahead and hit pause to jot down your thoughts and hit play when you're ready to check your work. So I noticed a problem right away with Marcel's histogram because he counted by tens. Do you see that? How he did bins from 0 to 10, 10 to 20, 20 to 30. And our bins went by fives. And so I realized there's a problem with Marcel's histogram. And that is if 15 is the threshold, I can't tell with this middle bar, I can't tell how many of them are over 15 and how many of them aren't. That's a problem. So Marcel's histogram isn't good. He's not correct. He only calculated the percent of sites that have 20 parts per billion or more. Using his histogram, you can't determine the number of sites that have 15 parts per billion or more of lead because you can't determine the exact values of the data from this histogram. Sorry, Marcel, it's just not right, man. So let's come back to our histogram and let's answer the question, the big question. Does the water system management of Greenville need to take action to reduce the amount of lead in the water? Remember, we said if 10% of the sites are over 15 parts per billion, we've got to take action on it. So go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. So I was taking a look and I was like, all right, these 3 bins are okay. It's these 2 bins that are a problem, right? That was like 23 and that was like 47. And when I added those together, 47 plus 23, I was like, holy crud, we have 70 sites that are over. And we said earlier that there were 250. So let's figure out what the percent is there. 70 out of 250. If I divide that to get a decimal, I get 0.28. Oh my gosh, 28% of the sites are over 15 parts per billion of lead in the water. That's a problem because we said 10% or more and you have to take action. We have 28% of our sites are over that 15 parts per billion. So yes, they need to take action. According to this histogram, 70 of the 250 sites samples have 15 parts per billion or more of lead in the drinking water. This is much greater than 10% of the sampled sites. So action is definitely required here. They're going to want to do something about that or people are going to start getting sick. Definitely a bad thing. So do you think this histogram is a good representation of the data? Why? Why not? Just jot down your thoughts. Was this a good representation? Go ahead and hit pause, jot down your thoughts, and then hit play to check your work. So I felt like this histogram was pretty good. It was a good representation, right? There were a large number of data points. We had 250 data points we were working with. We had our bins divvied up, counting by fives to make it easier to see the data. The more bins you have, then the more data points you have, the better the information you're going to get and the better your histogram is going to look, the easier it's going to be to figure out what's going on. So I felt like this histogram was pretty good representation of our data. I liked it. As always, guys, I hope you found this helpful and I hope you found this useful. If you have questions or concerns, please let me know. Come see me during office hours, ask me during class, email me. You know how it goes. And I'll see you guys soon. Bye.